Assalamu alaikum students, I am here again with a new method, that is the Fredholm alternative, and that is from the chapter number 4 that we were doing. Right now we have to solve this example. Show that the integral equation possesses no solution when your f of x is x, but it possesses infinite many solutions for f of x is equals to 1. In this question, I am going to explain you the Fredholm alternative method. This is the same way as we did in the start of chapter number 4, the general method. If you remember, I'm going to revise it again here for this example, within this example when it comes. So consider this integral equation that is given to you. Your kernel right now, k of xt sine of x plus t. Expand it using the trigonometric identity. Now you know that your kernel k of xt is the separable kernel, and this is the sum of fi of x gi of t. That is f1 G1 plus F2 G2 plus F3 G3 and so on. Right now this is the addition of two terms only. So F1 G1 plus F2 G2. F1 is depending on X and G is depending on T. And your lambda is right now here is 1 over pi. So I'm writing just them separately. F1 of X is sin X. G1 of T depending on T, so it will be cos of T. F2 of x is cos of x and G2 of t is sin of t. Now, if you remember in the start of chapter number 4, this lecture is already uploaded. If you want to review it, you can go back and you can watch this chapter number 4, first lecture of chapter 4. In this chapter, we derived it in detail. We know that our alpha ij, for writing d of lambda, we need our alphas. And for alpha, you know that alpha I of j is fj of t, gi of t dt. Or you can also write it fi of t, gj of t. It's up to you. So we need here alpha 1, 1, alpha 1, 2, alpha 2, 1, alpha 2, 2. Alpha I of j in our general system was, right now integration is from 0 to 2 pi, gi of t, fj of t dt. Our iteration is from 1 to 2 only. So it's going to be 1, 1, 1, 2, 2, 1, 2, 2. So G1 F1, G1 F2, G2 F1 and G2 F2. These are our possible combinations. Just plug in the values here. G1 is sin t, F1 is cos. All of them are on t, so just convert them in t as well. Integrate it. After integration, apply the limits of integration. I got these answers. This is up to you now. You have to solve this integration and get the answers. After getting the answers, we're going to write the determinant, d of lambda. This was for n cross n. Right now we are going to write for 2 cross 2. Our limit is until 2. See here? So we're going to reduce it until 2, like this only. Take this portion. So it's going to be 1 minus lambda alpha 1, 1. I'm just taking the value from here. Minus lambda alpha 1, 2, minus lambda alpha 2, 1, 1 minus lambda alpha 2, 2. Plug in the values of alpha 1, 1, alpha 1, 2, alpha 2, 1 and alpha 2, 2. After plugging in the values and simplify, I got this. Eigenvalues are given by d of lambda equals to 0. Take it equals to 0, get the values of lambda. You know that we are already given as lambda is 1 over pi. Since lambda is 1 over pi contains in the given integral equation, thus d of lambda is 0 and hence equation 1 will not possess unique solution. Now finding the eigenfunctions of the transposed equation. What is your transposed equation if you take your f of x as 0? So my integral equation will be reduced into this equation, f of x is 0 here. The algebraic system corresponding to the above equation given by beta 1 and beta 2 will be, if you remember, in our general method that we did, we got this system of equations, beta 1, beta 2. This system is reduced until the number 2, ij is taken until 2. So we will be having here 1 minus lambda alpha 1 1 C1 minus lambda alpha 1 2 C2 until here. Don't take the third one. For beta 2, minus lambda alpha 2 1 C1 plus 1 minus lambda alpha 2 2 C2 equals to beta 2. I took these here and just simplify them by plugging in the values of lambda 1 1, alpha 1 1, alpha 1 2, alpha 2 1, alpha 2 2. I got it. Here lambda is equals to 1 over pi, hence we get, if I plug in lambda is equals to 1 over pi, I will get C1 is equals to C2. Thus the corresponding eigenfunction Z1, I am just naming the eigenfunction for right now as Z1 of x. What will be my eigenfunction? Eigenfunction will be lambda I is equals to 1 to 2 Ci Fi of x. Like here your f of x is 0 and you just split it into some Ci's. If you remember, we did it in separable or degenerate kernel method. You took the x components out and you took the rest of the integral as Ci. So it's the same thing. Lambda summation I is equals to 1 to 2 Ci Fi of x. So it will be C1 F1, C2 F2. Just plug in the value of F1, F2 and plug in the value of lambda. Take the C1 common, you know that you got right now here C1 as C2 and lambda is 1 over pi, plug in the values, so you got this eigenfunction. When lambda is minus 1 over pi, your next eigenfunction, take it as Z2. I'm just giving it it's my own name, Z2. Lambda summation I is equals to 1 to 2 Ci Fi of x, same as this one. So take it as C1 F1 plus C2 F2, plug in the value of F1, F2, plug in the value of lambda, and we'll get this eigenfunction. The same way we did this right now. Now when f of x is x, our this integral 0 to 2 pi f of x z1 of x dx is, plug in the value of f of x, plug in the value of z1 of x, you can see that this is non-zero. And if I take this integral and we can see this is non-zero. So equation 1 will possess infinite solutions given by this. How we can write the solution? Fx plus c1 z1 of x plus c2 z2 of x. Just plug in the values here. After plugging in and simplify, I got this solution. And when f of x is 1, just plug in the f of x as 1 and put the value of z1, simplify, you got 0. Showing that f of x is not orthogonal to z1 of x and hence equation 1 will possess no solution. Now same way you are given with this assignment, you have to solve this equation the same way we did this Fredholm alternative method. After this method that we did, our next lecture will be based upon an approximate method of the integral equation when your kernel is not separable.